Okay, thank you. I'm impressed that there's at least anybody around for the last session. So I assume that this is an area that not a lot of people are terribly familiar with, self-assembly and the tile assembly model. So a lot of the talk is going to be a real quick tour through, a kind of a background of the area and related results. So kind of a high level, relatively fast moving, but hopefully you can get something out of it and understand the area at least a little bit. So what we're interested in is what we call algorithmic self-assembly. And it's a subset of self-assembly. And self-assembly is a process where you start with a large collection of relatively simple components in a disorganized state. And those components autonomously combine to form more complex structures. And what I mean by that is there's no external guidance, and the components only experience local interactions throughout the process of self-assembling. Our inspiration comes from nature. There are a lot of natural self-assembling systems, things that make crystals like snowflakes, a variety of biological components self-assemble from their constituent proteins and other components. So, but like I said, my work is focused largely on what we call algorithmic self-assembly. And this is a subset of self-assembly that's based on computational theory. And in algorithmic self-assembly, our goal is to design the components and the systems so that as self-assembly occurs, the components are forced by the design of the system to execute intrinsically some algorithm, and we'll see some examples of that. So it's kind of motivated by some work that has been done with DNA tiles, DNA components. Algorithmic self-assembly has occurred to make things like binary counters. So as these tiles combine, they perform binary arithmetic and count in binary. Here's an example, might be hard to see, but as these tiles combine, they're forming a pattern known as the Sierpinski triangle, so a fractal structure. So that's kind of the motivation for a model that came along known as the tile assembly model. It was based on, originally DNA molecules being made by Ned Seaman. Kind of putting them in configurations, getting them to build themselves into configurations that aren't the typical double helical structure of DNA. And Eric Winfrey, a computer scientist, recognized that, well, we could look at these kind of complex three-dimensional molecules, and we could more abstractly think of them as two-dimensional squares. And if we extend the DNA off the ends a little bit to unpaired components in these tiles, we'll have what we call sticky ends of DNA that want to bind with complementary subsequences. And we can further abstract away and just think of these as square tiles with glues on the edges. So that's the basis for what you call the abstract tile assembly model. And so we're abstracting away the thoughts of the underlying molecular system, and instead just coming up with an abstraction where we just think of the fundamental components being two-dimensional squares, and on the edges, what we have are what we call glues. Glues have two components. They have a strength, which is just an integer value, typically like 1 or 2, and then some type, and I'll represent that usually here in the talk by a color, and the number of tabs will represent the strength. Tiles, like this tile here is a label L. That's not functional. It's just for convenience of notation. In the model, tiles can't be rotated. All that really matters is they can't rotate relative to each other, so east always sticks to west sides and north to south. And that's something that can be realized in the DNA setting. But again, we're interested in just an abstraction here. So tiles can't be rotated. And then you're allowed, so each kind of tile, we call it a tile type, is the full definition of a tile with the glues around its edges and its label. So you're only allowed a finite kind of different types of tiles. But as self-assembly occurs, you get an infinite supply of each one of those copies of the tile types. And so the way the assembly process works is when tiles are floating around and they bump into each other, if they have matching glues, then they bind with the strength of the glue. So these two tiles would bind with strength 1. These two would bind with strength 2. And for instance, these two tiles which have mismatching glues, they're not the same, they wouldn't bind. There would be no strength of binding. And so the way that self-assembly occurs in this model is that it begins from a seed, either a structure or a single tile, and then tiles attach one at a time, and they attach to the growing assembly if they meet a minimum threshold. If the glues with which they can bind sum to a strength that meets a minimum threshold, then they're allowed to attach and stay attached. And so, so that's the basic premise of how the tile assembly model works. And so we define a system in the ATAM as a triple. The first component is a set of types of tiles. The second is the seed, which is just a set of those tiles in some configuration. That's the configuration we get to begin from. And then the minimum binding threshold. How strongly do tiles need to be able to bind? How much glue strength do they need to be able to bind with to stay attached to the assembly? And then as tiles attach to a growing assembly, the particular sequence that they follow as they attach, we call this an assembly sequence. And we'll see an example here of the fact that sometimes multiple assembly sequences are allowed by a system. For instance, if our system has tile types like this, and this one right here is our seed, so perhaps we've got 2 copies of the seed. We can think of, in parallel assembly happening. We have 2 copies of the seed, and its strength at the temperature value of 2, the minimum binding threshold, we'd see that either one of these things could happen. A tile of this type could attach here, a tile of this type here. That'd be a valid attachment, but it's a different sequence. And as these assemblies grow, we can see different sequences being followed, but it's still resulting in the same tiles being placed in each position. And all these were able to bind with a single strength 2 glue. And now we can see that a tile could attach here with a combination of a 1 + 1, 2. So tiles could come in and attach, again, perhaps a different sequence. But nonetheless, in this particular example, the interesting thing is that any assembly sequence that can be followed, you always result in the exact same assembly being built. All the same positions get tiles, and they get the same tiles. So we say that's a directed system. It's clearly easy to make systems that are not directed. The different assembly sequence could yield different things, but we're especially interested in directed systems. That's what I'll focus most of my talk on. So now to talk about how the model is actually computationally universal and how we can get it to compute algorithms. Let's see how we can simulate a Turing machine. For ease, I'll just simulate a Turing machine with a one-way infinite tape, and we'll just look at the fact that what we could do is, we have our initial tape, our input, and then we assume it's infinite off to the side. Well, we could have tiles that encode the initial input segment, and we could assume that we could set up so the glues encode. They have an encoding of the values of each tape cell, and then for the unique tape cell that has the tape head at it, the glue, we could also encode information about what state we're in. So now, if we look at it, we can see exactly where the tape head is, what the state is, and what the input of the tape is. And then, say our Turing machine, had a step that moves it to the right and changes the value of the cell and goes to state Q3. Well, we can design our tile types based on the definition of the Turing machine, so that the tile that attaches here has glue information that tells that we're going to move into state Q3 and the head should be over here, and that we're now going to be a 0 here. And then so the tile that can attach here knows that now we're in state Q3 reading a 0, and the rest of the row can fill in. And we get the next kind of configuration of the Turing machine. For ease, what I've done here is I'm going to just make each row, each time we grow left to right, I'm going to extend the tape a little bit. You can also be more succinct and only extend the tape by an extra tile when needed if the head needs to move off to the side. But in this particular type of simulation I'm going to show, each row is going to grow first left to right, and then we'll grow back right to left. So what's going to happen here, if the Turing machine performs another transition that moves the head to the right, well, this row that's growing back in this direction, basically what it's going to do is it's just going to kind of remember the information that the head needs to move right and grow up another row and then pass that information over. So as this row grows over, we get the correct location of the head. And then obviously, analogously, if the head moves to the left when the row is growing left, it can fill in and propagate the information correctly. So in this way, we can design a system that simulates a Turing machine, and in fact, at each row of tile growth, we can see the state, the configuration of the Turing machine at that time. So this shows us a real quick example of how this model is Turing universal. And so that's one kind of universality that this model possesses. And now I'm going to talk about another, which is called intrinsic universality. Intrinsic universality, I'll define like in terms of models. And we'll say an intrinsically universal model is one in which there's some system in that model that's capable of simulating all other systems within that model. The simulation might require scaling, and that could be a space or time-based scaling. But there has to be some function that maps blocks of the simulating system to individual components of the system that's being simulated. And the really important thing of intrinsic universality is the fact that the dynamics of the simulated system have to be simulated. You don't just you don't just achieve the same end result, but it has to be the case that the simulator, maybe just modulo the scale factor, actually exhibits the same dynamics, so the same pattern of behavior. So intrinsically universal models include Turing machines. There are Turing machines that can simulate other Turing machines in this way. There are cellular automata. If you've heard of cellular automata, there are those that can simulate all other cellular automata. And we showed in Fox 2012, actually, that the abstract tile assembly model is also an intrinsically universal model. So that's going to kind of be the basis for the result that we've kind of extended here. And so a little description of that. What that means is there's one tile set there exists a tile set in the ATAM such that if you give me any arbitrary other ATAM system, I can take the tiles of that universal tile set, we'll call it U, and I can arrange them into a seed configuration such that if I put that seed in and I just throw in tiles only of U, then the assembly that occurs will mimic that of the system that you gave me as input. And it has to, importantly, simulate every possible assembly sequence of T. It has to be able to do everything that T could do, okay? So here's an example of some system T, some tile types, and maybe here's the seed, and perhaps, here's a pattern of growth, and this will be important in a bit. We'll mention, so maybe in this particular configuration, one of two different tiles could come in. Either this one could come in, or this one could come in, and they have different, we call input sides, right? They have their binding using different locations, different sides of the tile to come in. Well, if one of them comes in, okay, so that's our system T. It's non-deterministic. It's not directed. How is that simulated by by U, the universal simulator? Well, what's actually going on is there's a big block of tiles representing each tile of T, and they contain a vast amount of information that I'll describe real briefly. But essentially, we call each such block of many tiles of U, we call them a super tile. And real briefly, to discuss how those form, when I'm given my arbitrary T and I have my universal tile set and I make the seed, that's the only way that this system, this universal set of tiles, has any idea what it's supposed to do. So all of the information about the system being simulated has to be encoded in that seed and then passed around through the growing assembly, kind of like a genome going through cells. They differentiate. And so, but an important thing to note is the scale factor has to remain constant throughout the simulation. Depending on the system I'm simulating, I might have a different scale factor, but given any particular simulation, the scale factor isn't allowed to change. Okay, so the important thing here is that as we saw, from the really brief example I gave before, tiles could have different inputs, different input sides, and as our super tile grows, it has to be able to aggregate information from different adjacent super tiles to figure out, bring it together, perform a computation, to figure out what type of tile it should be simulating. But it turns out that in general, it is uncomputable to know, given a particular type of tile or a location, which sides will be input of a tile that eventually gets placed there. So given that, the simulator now has to be able to handle some trickery. It has to be able to combine information from any arbitrary subset of sides, which could be used as input to determine what tile goes there. But it has to also be able to accommodate the fact that the arrival of information to those sides could be an arbitrary ordering, because different assembly sequences could be followed as these super tiles grow. One of them might grow faster and one slower in one assembly sequence, and vice versa in another. So the ordering of arrival and which ones will ever arrive is unknown as a super tile is growing. So that created some difficulties in the initial construction. And so to accommodate that, what we did is we used these things we called points of competition. Here is there are many of them in our construction, but they're especially on the corners. And for instance, one of the things that we did was we made it such that as a super tile is growing from this direction, it basically is racing to place tiles and points of competition. If it's the first one to place a tile there, then the protocol dictates that growth beginning from there goes around and aggregates information and kind of determines the evolution of the super tile. But it's all based on timing, of basically who gets there first. So what that does, though, unfortunately, we noticed, is that even when we're simulating a system which itself is directed, always places the exact same tiles in all the exact same places, the simulator wasn't directed, right? It has these timing-based issues that could allow different tiles to appear in different places. So that made us question. It said, is this non-determinism, is it fundamental? Does the simulator need this? And the answer is yes. And so I'm going to sketch that result real quickly and tell you how we achieve that result. So the main theorem of our paper is that the class of directed ATAM systems is not intrinsically universal, meaning there is no simulator that can simulate all directed systems and itself always be directed, always placing the same tiles in the same locations. The proof is basically a proof by contradiction. So if you assume that there is such a universal simulator, given that, we can design a system that we can prove can't be simulated by a directed simulator. And so I'm going to just go through a real fast sketch of how it works. So essentially, it's a modular construction. From the seed grows some module that's going to grow out infinitely far to the right, and its whole job is just to grow out some spacing and provide some information to allow new modules to grow up from the top and kind of increment, one after the other, feeding input to them. We call them a series of iterations, so they're iteration I to infinity, and each one is made up of sub-iterations. Again, not going to go into ton of details, but we're really focused on what a sub-iteration is. So a sub-iteration is really the key, but the fact is that there's an infinite number of them all getting different inputs that makes this work. The structure of a sub-iteration has 3 main modules, and the real key is that they're designed in such a way that they're all performing computations, but essentially they're performing computations that can't be discerned by the other, and that was kind of the trickery involved here. We had to find ways to hide information so that there's no way to pass information around through a growing assembly, even given a scale factor of a simulator. And the basic way we do that is we use constrained room for inputs. So the amount of the space given to input of a module might be smaller than another's, but then the space that it's given to like the tape space it's given to perform a computation is larger than another. And so we have these mutually exclusive computations, and we can guarantee these using some really nice complexity results, and we can guarantee the bounds of space needed by certain languages, and we can ensure that computations can't be done by different modules can't do each other's computations, and so they don't know what the results will be. And the basic goal is that when this module and this module, when they're done with their computations, they put the string of bits facing each other that correspond to their outputs. We call this the bit alley. And then the one other main the computation here is actually able to do the computations of these two plus an extra one. It performs both of their computations, and it figures out what their answers will be, and if and only if every single bit that they put across differs from each other, it will grow up and make an arm grow down in between. Okay, so the idea is this bit alley, when these two computations put bit strings, whenever the bits are equal, they'll cooperate to place a tile, and when they're unequal, they'll leave a gap. And the key is, if and only if there's a gap all the way through, all bits mismatch, then an arm will grow through, and we can guarantee that. And it will happen once per iteration. And so why does that break any simulator? Anybody who wants to simulate this is going to fail, and the reason is essentially because for the simulator to be able to mimic the behavior of cooperation across the bit alley, it has to be the case that some portions of the simulator grow to within a single tile-wide gap or less. They could grow to be adjacent to each other, or a single tile-wide gap to allow potential cooperation. However, we can ensure that the arm, any representation of the arm requires more than a single bit. So essentially, as these multiple modules are completing their computations, the left and right never know if they're actually going to need to cooperate with each other, so they have to grow out and get really close together. But the arm that's going to grow down, if in the situations where it does need to grow through, is going to be too wide to be able to get through the gaps. And then there's a lot of other technicalities with it, because eventually these gaps, these bit alleys get longer and longer. They become arbitrarily long, and with a fixed scale factor, the arm can't encode all the bits, so it can't know how it might have to dodge components. So essentially, an arm is destined to have to crash and do some kind of point of competition non-determinism. So, so that's a real high-level sketch of how we can force any simulator into having to compete and use non-determinism to simulate the system, and thus showing that all directed systems can't be simulated by a directed simulator. We had a nice secondary result. We had some components that we think will be useful for future work. Basically, just how we can show that simulators can't get asymptotically greater space computations. We don't have time to go into those details, and we're in the last session, so I will just stop now. I want to thank my co-authors, and thank you for coming to the last session. If you have any questions, I'll be happy to answer.